first ones that we have are these here. And it is very tempting because when we covered this last time, I talked about cross multiplying. And that in the textbook it does say, and in our notes coming straight from the textbook, it does reference these as cross multiplying. And it does work for this here. It does work for this problem here, but it only works for this problem here. Because once we start getting more than 2, we can't just cross multiply. Cross multiplying is a nice trick that works when we're having 2 ratios, 2 fractions equal to each other when we talk about proportions. It's a nice little trick that works. And the reason that it works is because what we're doing is actually using the least common denominator. And if we actually start off and look at these using just the least common denominator, when we get to more than 2, when we have 2 things on one side and 1 on the other, it still works just fine. And really what we're looking at, just like with complex fractions, we're trying to see what do I need to multiply everything through, each part of this equation by, so that all the denominators cancel each other out. And we also cannot have the denominators be 0. So here, the only place it could be 0 is our 3x minus 1. So if we wanted to see its restriction, well, we can just solve for the value of x. These would cancel, telling me 3x is equal to 1. Divide by 3. So if we get x as the solution of 1/3, we know that doesn't work because x cannot be 1/3. So that there is just so we can kind of know what the restrictions are ahead of time. Any questions on this so far? Now looking at the denominators, we only have 2 of them. One of them is 3x minus 1 and the other is 4. So to get all the denominators to cancel, well, we are going to need to multiply both sides by 3x minus 1. Do we need anything else? The 4. So we're multiplying both equations by 4 times 3x minus 1. Well, on the one on the left, the 3x minus 1 and 3x minus 1 will cancel, leaving us with, well, 6 times 4. And really, we could have just said 6 times 4 is 24 and written that down. That shouldn't be too bad. On the other side, the 4 and 4 will cancel, leaving us with 3 times 3x minus 1. And realistically, if you wanted to go on and multiply through with the 3 to get 9x minus 3, that would have been perfectly fine too. Because if you feel comfortable at this point multiplying 6 and 4 when you simplified and the 3 times 3x minus 1, that's perfectly fine. Because we could have gone on and said 6 times 4 is 24. 3 times 3x is 9x. 3 times negative 1 is negative 3. Now we just need to solve by first adding 3 to both sides. Which tells us 27 is equal to 9x. Then divide by 9, telling us x is equal to 3. Is that our restriction? Well, no. Our restriction was 1/3. So x equals 3 is the solution. And that's it. Questions on this here? So again, it is a good habit to get into looking at the restrictions first. Because if we know what the restrictions are, we can know what the solutions for x cannot be. And it's really looking at what values of x are going to make the denominator 0. Now with the x by itself over here, well, we know x cannot be 0. Even if it was x squared or 5x cubed, that would still just be 0. And again, if we wanted to solve it, well, we set it equal to 0. Well, that's solved. X can't be 0. Even if it was 5x, well, I would divide both sides by 5 and still get that x is equal to 0. Because if I have more than one thing multiplied together to equal 0, one of them must be 0. So if it's just a single term, we don't have addition or subtraction, most likely it's telling us that x cannot be 0. Now the other one that we have is the x minus 4. We can get it later. For this here, x cannot be 4. Because 4 minus 4 is 0. All right. Okay. Come on. All right. Now the next thing we need to do is find the least common denominator, what we're going to multiply everything by. X times x minus 4. Yes. So here the x and x will cancel out. The x minus 4 and x minus 4 will cancel, leaving us with so we can go on and multiply through. Because if you do feel comfortable doing the 5 times x minus 4 and distributing that, that's perfectly fine. Because that's not too much to juggle, especially when we talk about quadratics, where we have 2 of those, x minus 4 times x minus 7. It might be good to rewrite that so we don't lose any terms. Here we can go on and distribute the 5. Well, we can subtract 5x from both sides, telling us that negative 20 is equal to 2x. At this point here we would divide by 2, telling us x is equal to negative 10. Was that one of our restrictions? No. So that's our solution for this here. And that's all we have to do for these. Any questions on any of these here? Okay. Luckily with these here, finding the restrictions for x plus 1 and x plus 7 is not too bad. Because for x plus 1, it would tell us that x cannot be, well, negative 1. And for x plus 7, we know x cannot be negative 7. And really, if we had a number in front of x, it's not too much more difficult than that, because we would subtract the number and then divide by whatever's in front of x. So now we just need to see what we're going to multiply everything by. For the 15, we're going to multiply by, we know x plus 7. What else? X plus 1. I really need to bump those down just a hair, so I have a little more room to write above them. And the reason we do that is because here, the x plus 1 and x plus 1 will cancel out. Just like how we had yesterday where we showed you where we can write it with those show over the top of each other and they simplify. That's essentially what we're doing here. The same is true for this x plus 7 and x plus 7. Now this one here, it might be good to go on and just write x plus 3 times x plus 7. Because it might be a little bit difficult to see how this multiplies out. Because if you are able to see that this here multiplies out to x squared plus 10x plus 21, that's perfectly fine. But again, that's a lot of terms to just stick together. On the other side, we have 15 times x plus 1. So if it's, again, multiplying, and especially how it's written here, is a lot to look at and try to keep track of, go on and write it back down. That we have 15 times x plus 1. Because again, in here or any other class, you're not losing points because you write out every step. But if you have difficulty doing a lot of those or skipping steps in your head, write it out. Because you will lose points if you lose track of signs or drop something where you're not supposed to. Because now we can go on and multiply through. X times x is x squared. X times 7 is 7x. And then we can do the same thing with the 3. Plus 3x plus 21. Now at this point here, we can combine our like terms. X squared plus 10x plus 21 is equal to 15x plus 15. Well, it doesn't matter which one we do first. We can subtract 15x from both sides. So tell us that x squared minus 5x plus 21 is equal to 15. And we can subtract 15 from both sides, telling us x squared minus 5x plus 6 is equal to 0. Grab that. I need to repin that back to the bottom because now at this point here we need to solve the quadratic x squared minus 5x plus 6 is equal to 0. There's different ways we can do it. One of them that really we haven't been doing in here at all is the quadratic formula unless we absolutely had to. The other way was factoring, yes? Minus 5x. And then there's one way that we've actually completely forgot about. We can graph it. X squared minus 5x plus 6. Because graphing works well if we do have whole number answers. It will find decimal answers as long as the decimals are nice. When I say nice, we're talking about like 1/2, 1/3, something that can actually be written as a fraction. If it's an irrational number, it's not going to be as nice. So we can actually graph it. And let's see. Up. There and there. If we go second graph, again, we're looking for y is 0, and the x values where y is 0 are at 2 and 3. So that tells me x is equal to 2 and 3. And a way that we can write it is 2 comma 3. And is 2 or 3 one of our restrictions? So that's it. Because if we had graphed it, or not graphed it, factored it, we would have gotten x minus 3 times x minus 2 is equal to 0. So x minus 3 is 0. X minus 2 is 0. Plus 3 plus 3 plus 2 plus 2. So x is equal to 3 and x is equal to 2. I mean, we could have gone and got the exact same answer doing it this way here. And I also would not advise solving once you get to factoring like that, because realistically you're trying to keep 2 separate equations in your head at the same time. Might not be the best, especially if on a test. But again, if we get whole number answers, if it's factorable, it's graphable. We can actually get it by graphing if it is factorable, and if it's factorable, it means I could have got the answers by graphing. The only time it will be a little harder to find them graphing is if there's a number in front of x squared, because that means one of the answers is going to be fractional. But that's it. Questions on this here? I think y'all feel comfortable with these here, especially when we've got just two. Let's look at this one here. And actually, surprise, surprise, this actually isn't any, it's a little different, but not by too much. Now, we need to find the restrictions. 4 and 3. Because 4 minus 4 in the first one would give us a denominator of 0. And the second one, 3 minus 3, would give us a denominator of 0. We can't have either one. Now, these problems here is where cross multiplication fails. Because cross multiplying is essentially multiplying the numerator by the denominator of the other side. Well, wait a minute. On the last one here, what we did, essentially what we did, yes? Okay. So we come over here, so we can multiply the denominator by the numerator of the other side. Well, I don't quite have that because I've got two denominators on one side, and on the other, I technically have one, but it's 1. Well, that's completely fallen apart, yes? So that's why I don't teach that way, or with that method. It's nice for the first ones that we did, but okay, now that we've got to this here, we need to go over a different way to actually do it. So the trick works nice in some cases, but it doesn't work all the time. I don't like those methods. But here, what did we do on the last one? We multiplied it by what we have in the denominators. So here we're going to have our y minus 4 and y minus 3. And some would rewrite this again and then have those multiplied in. If we don't have to rewrite it, I'm all for not rewriting it. Now, on the first one, well, the y minus 4 and y minus 4 will cancel out. They'll simplify out. In the middle one, the y minus 3 and y minus 3. And well, in the last one, it doesn't have a denominator that will simplify out with anything. So what we're left with is 4 times y minus 3 minus 3 times y minus 4 is equal to y minus 4 times y minus 3. Now we do need to be careful with this one here because it might be tempting to have multiplied the y minus 4 in the middle by 3 and gotten minus 3y minus 12, which isn't quite right. Because if you'd gotten for the middle one here, 3y minus 12, it's a little bit off. Yes. It's the negative. And that's where sometimes we need to be careful, because if looking just here, it's very tempting to just multiply both of those by the 3 and forget about the minus in the middle. So sometimes, especially when we deal with negatives, it might be good to rewrite it to keep track of those signs. Here, we multiply by the 4 and get 4y minus 12. Here we're multiplying not with just a 3, but with the negative 3 y plus 12. And if you do feel comfortable with doing that and eliminating at the same time, go on and do it. But if you want to make sure that you keep the signs right, it's sometimes good to write it out. On the other side, we're going to have y times y, which is minus 3y minus 4y plus 12. Now at this point here, we can combine like terms on both sides. 4y minus 3y is negative 12 plus 12 is 0 equals, well, we'll have the y squared minus 7y plus Any questions on this here? Okay, well, we can minus y from both sides, which tells us that 0 is equal to y squared minus 8y plus 12. And at this point, we can graph it or factor it, either way. And if this is on the ACT and they gave you a problem like this and you got to this point here, is there anything in front of y? Or the y squared? Well, no. So we're mainly looking at the factors of 12. So it's either going to be 1 and 12, 2 and 6, 3 and 4. If we factor this, yep, y minus 2 and y minus 6. Well, looking at this here, we know the values of y have to be what? 2 or 6. Actually, at this point, solving this was almost the exact same as finding the restrictions at the beginning. Yeah. Which I find sometimes ironic when I teach this, because at this point I'm not writing out the restrictions, but we do go through and write out how to get this here, even though that's essentially is the exact same thing, but it is sometimes nice to see written out. And are either one of these our restrictions? No. Because our restrictions were 3 and 4. And that's it. The one thing we do need to be careful with is problems like this here. Because it's very tempting, and I've seen it many, many times, to go on and say, we're going to multiply all of these by x, x plus 1, and x squared plus x with all three. But the middle term, the x squared plus x, it's not factorable in two sets of parentheses. But what does it have? It has an x in common in both, yes? It has a greatest common factor. And if I factor that out of the middle term, as we're only going to be affecting the middle term, because the first one, the x plus 1, is as simplified as it gets. The x is as simplified as it gets. But the x squared plus x does have a greatest common factor of, so we have x times. So if I had to use the x times x plus 1 times the x squared plus x, I have added an extra factor of x and x plus 1. And any extra factors, especially with these variables that we add, increase the degree by 1 for each one that we add. So if this had worked out to be linear, if we'd have used the correct ones, adding those two is taking it from a degree 1 to a degree 3. We're now having to solve a cubic equation. Or just having 1 would take it from a linear, when I say linear, something like this here, where the biggest power with x is 1, to a quadratic. And any one of those that we add will actually work out to be one of the restrictions. It's adding that in. It's adding the restriction into the equation. So it doesn't help us. It makes the equations harder to work, and it gives us solutions that don't work. So it's going to make it harder on us. So here, well, the x's that are by themselves tell me x cannot be 0. And for each x plus 1, it would be -1. Okay. Well, we can see that we do need to multiply all of these by and now just doing the x times x plus 1, if we look at the middle, because that's the one that had the x squared plus x, with it factored, well, both of these actually cancel out with both of those there. So I didn't need it. I didn't need that extra x squared plus x, because it's already contained with the other two. And the first one, the x plus 1 and x plus 1 will cancel. Over here, the x and x will cancel, which leaves us in the first one with 2x minus is equal to plus 3, because if we distribute the 3 go on through, 3 times x would be 3x, 3 times 1 would be plus 3. Well, the degree for this all is 1, yes? The biggest variable that we have has a 1 power. So if we'd actually multiplied with the x squared plus x, the biggest power wouldn't actually be 1, it would have been 3. We'd have had to deal with a cubic. And 2 of those solutions for the cubic actually would have been 0 and -1. Doesn't help. And at this point here, it's actually not that bad, bless you. So we would subtract 2x from both sides. Well, we'd go the other way, but yes, because we want x by itself. Because the only time we want to get everything on the same side is if the degree is greater than 1. Because when we deal with quadratics, cubics, quartics, 5th degree, 6, and on, those higher degree polynomials, we set it equal to 0 and solve that way. But here, if it's a degree 1, get the variable by itself, and it'll solve out. And we get that x is equal to -4. Is that one of our restrictions? Nope, so that's the solution. That's it. Questions on any of this here? Are these a lot easier than what y'all thought previous? Yes. And a lot of the times when we have struggles or kind of hit a hitch with these here is just like with this last one, multiplying through by too many terms is going to make these harder than they need to be. I don't think we have too many more of these. 2 more? 4, okay. Because I don't think y'all need to see too many more of these. Because I feel like y'all have gotten the hang of this now. Now looking at these here, I'm trying to see which one would be good. Let's see here, 5, this one? Yeah, let's look at this one. I like this one. Because the reason I say that's not because there's something tricky in it and what we're doing. There's a nice little nugget that does work out well. Let's look at this 2x minus 2 and x squared minus 4. We can factor those. We can simplify them to make it easier to work with. What can we do with the 2x minus 2? We can factor a 2 out of both of those, yes? And x squared minus 4. 2 and what do we notice about the middle term? Yep. Because we have what? 2 over 2 times x minus 1, yes? And a lot of the times, especially with addition and subtraction, we saw those common factors before we added and subtracted. We didn't want to eliminate them because we needed the denominators to be the same, yes? Or for it to eliminate out. Now, in the rest of the denominators, does any one of them have a 2? Because we have it in the middle, yes? Well, 5 doesn't have a denominator, correct? Does the 3 over x plus 2 times x minus 2 have a greatest common factor of 2? So is there any reason for me not to simplify the 2 over 2? No, we could actually do that. The only reason I wouldn't want to is if here or somewhere over here, we had the 2 in the denominator. is if I had to multiply through with the 2 because of one of the other ones, okay, we would need it. But here, do we actually need it? No. And that's why I was saying I found this one interesting, because that 2 is unnecessary. We could multiply by it, but then in the end, we would actually be dividing or removing that 2 anyways. So really this here, this 2 cancels out, really just giving us 1. Actually don't need it. And it's also telling us x cannot be 4, 2 or negative 2. We can say plus or minus 2. Now we do need to multiply each one of these by our term. So we'd have x minus 1 times x plus 2 and x minus 2, x minus 1, x plus 2, x minus 2, minus 1, x plus 2, x minus 2. Ooh, we're going to get a nice, I think it's an interesting equation. Is if we look at the 5, well, any of those 3 simplify out. No. So that means the degree of this is going to be what? Because in the first one, we do have an x times an x times an x. We have 3 of them, so it's going to tell us we have a degree 3. In the middle, the x minus 1 and x minus 1 will cancel out. And the x plus 2 and x minus 2 cancel out in the third one. For the first one, I would not try to do any multiplication at this step, except for the x plus 2 and x minus 2. And it's really at this point not doing any multiplication, because where did we get the x plus 2 and x minus 2 from? Well, the x squared minus 4. So I wouldn't consider that so much multiplying as it is we're just replacing it back with where we got it from. Minus, well, in the middle is still the x plus 2 times x minus 2, which is our x squared minus 4 is equal to 3 times x minus 1. All right. Now we need to do some multiplication and simplifying. Now I wouldn't distribute the 5. Let's wait till the end for it. Once we finish all the multiplications at the beginning. All right, here. There we go. So we're at 5 times. Here, x times x squared would give us x cubed minus 4x. Negative 1 times x squared is negative x squared plus 4. Minus x squared plus 4. Because for the middle one, we can go on and distribute that negative and get this here. And lastly, we can multiply through with the 3, which gives us 3x. Okay. All right. In that first set of parentheses where we haven't multiplied the 5 with yet, are there any like terms? Well, we don't, do we? So we can't really combine anything. If we wanted to, we could rewrite this entire thing and have it in standard form. But is that really changing anything? No. If this was me and I was working this, I wouldn't take a step to rewrite it. I would go on and multiply the 5 and reorder it as I multiply. Because 5 times x cubed is 5x cubed. Well, in standard form, x squared would technically be next. 5 times negative x squared would be negative. So it's really multiplying it by the 5 and just kind of bumping it up to its correct spot. 5 times negative 4x is going to be 20x, and 5 times 4 is plus 20 minus x squared plus 4 equals. Now, if that's was a bit of a stretch, go on and just multiply it by the 5 and leave it as it is, and then rearrange them in the next step. Okay? And again, if any of these steps, it's a bit much to try to keep straight, just rewrite it with it in standard form and then multiply by the 5. Well, at this point here, we need to combine our like terms, which would give us 5x cubed minus 6x squared, because the negative 5x squared and negative x squared give us negative 6x squared, minus 20x plus 24 is equal to 3x minus 3. At this point here, we do need to get everything on the same side of the equation. So we can subtract 3x from both sides. This tells us that we have 5x cubed minus 6x squared minus 23x plus 24 is equal to negative 3. Then we can add 3 to both sides. Five x cubed minus 6x squared minus 23x plus 27 is equal to 0. So, do we have any methods for finding the solution for this here? Well, we do have factoring by grouping, and that's finding the greatest common factor between two of them that we can factor out, and then getting the same thing, factoring it out again. Or, we can graph it. Clear. I think it 5x cubed minus 6x squared minus 23x. I want to say minus 27, or is it plus 27? Graph it. So we do have these points here. I don't think that's quite at negative 2. Second table. Not quite. Graph. One of those. Now, point here it is, we are able to actually solve this because most likely our factors for this are plus or minus 1, 3, 9, 27. Well, we know those aren't it. Then we'd have 1/5, 3/5, 9/5, or 27/5. Well, 27/5 is actually going to be greater than 5 or less than negative 5. So these here are technically out. 9/5 is either going to be just slightly less than 2 or negative 2. And if we look back at the graph, okay, we have greater than 2. Neither one of those look like they could work. 3/5, well, 1/5 is, I think, the best option that we have. And what we can say is, because if we look at this here, that there looks like it could be close to positive 1/5. 5, negative 6, negative 23, and 27. 5. 1/5 times 5 is 1. Negative 6 plus 1 is negative 5. 1/5 times negative 5 is negative 1. And this here would give us negative 24, which does not work. Darn. Well, we can also try 3/5. Almost a few more. So 3/5. 5 times 3/5 would give us 3. 6 plus negative 3 would be negative 3. Okay, that doesn't work either. Well, second, calculate 0. I'm trying to remember what these are off the top of my head, and I don't remember. It's left down. Okay, that's far enough. Boom, boom. 2.136363. Okay. It doesn't look like this has nice solutions at all. I'll finish off by saying there's not going to be something like that on the homework that I'll give you as y'all head out. But that one there is a little funky. I'm going to look back at it and see kind of what happened, if the solutions are actually that ugly, which I don't think they are. Gosh. Yep. You're welcome.